Today we're going to talk about a formula that was created a long time ago by Galileo, and it's aptly named Galileo's formula. And essentially what it involves any object that's under the influence of gravity. So that could be a lot of different things, but so essentially we'll be looking at an object under the influence of gravity. And so in general, we'll look at an object that is maybe thrown, and generally we'll just look at thrown vertically, just directly up into the air, or maybe it dropped in some way. So both of those are examples of when an object would be under the influence of gravity. If I drop my pen, that object is under the influence of gravity. So the formula, what Galileo's formula gives, it gives the height of the object at any particular moment in time. So as a function then, that's what we want. We want at any moment in time, what's the height of the object if it was dropped or if it was thrown. And here's the formula that Galileo came up with. He said that the height as a function of time is given by the initial height, which we're going to say h sub 0, or usually that's read out as h naught, the initial height, plus the initial velocity times time minus gravity divided by 2 times t squared. Okay, so again with this one, the h naught, that's the initial height. So essentially that's the height at time 0, the initial height. V naught is the initial velocity, so the velocity at time 0. And notice with this initial height one, if I do plug in 0, notice that these terms, go to 0, and we're just left with the initial height. So that kind of makes sense for that one. And G is gravity. G is the acceleration due to gravity. Now, of course, that's a constant. Our acceleration due to gravity on Earth is a constant. Depends on the units that you use, but it is 32 feet per second per second. Okay, and some people write this as feet per second squared. I like to think of it as feet per second per second. So essentially, if I drop a pen, then after 1 second, it's traveling 32 feet per second. As it travels one more second, then it would be traveling 64 feet per second. So after every second goes by, it picks up speed of 32 feet per second if it was dropped. And if we look at some other popular units, meters per second are also pretty common. Okay, so those are basically the two gravity constants that we're going to look at. And notice that acceleration due to gravity really should be negative because the force is downward, but we actually already have a negative up here in our equation. So in the end, we'll think of this as a positive number so that we're subtracting this. Now notice if I were to graph this, it would always be a downward parabola, like so. Okay, so sometimes we'll be interested in a few different things. This would be essentially the height at time 0, the initial height. The initial velocity would be the slope of the tangent line at that point. Okay, and then of course our gravity is always going to be a constant number. Now you might be wondering a few things like, well, why are we dividing gravity by 2? Kind of where is this formula coming from? Well, let's take a look at, maybe I wanted to know the velocity at any moment in time. Okay, so if I wanted to know that, of course if we have height, the velocity is the derivative, right? The derivative is the rate of change or the slope of the tangent line. So in this case, that would be the velocity of the object. Now if we do that, okay, so h naught, that's a constant, so that would be 0. The derivative of v naught t, well, we can think of the constant multiple rule. That's a constant, so we can think about pulling it out in front. The derivative of t with respect to t would be 1. So I would just have v naught minus, now I'd have g over 2, because again that's a constant, and the derivative of t squared is 2t. So notice what I have, then I have v naught minus g times t, because the 2's cancel out here. Okay, so notice if I were to plug in 0 here, that would be 0. That would be my initial velocity, the velocity at time 0. And also notice what this is saying. This is saying my initial velocity, well, my velocity is going to be whatever it was initially minus whatever gravity has done to it. And of course, the more time that goes by, the more effect that gravity has on it. Okay, well, also notice that if I wanted to look at the derivative of velocity, so velocity is how the height is changing, right? So the derivative of velocity would be how the velocity is changing, and that would be the acceleration of the object. So I'm going to go ahead and call it a of t. So the acceleration would be one more derivative here. It would be the derivative of our velocity. This is a constant, again, so it would just be 0. And the derivative of minus gt would be negative g. Okay, so notice then what that is. That's the acceleration due to gravity. So one actually could also start with the knowledge of the fact that the acceleration due to gravity is a constant number, and we could work our way backwards. We could say, okay, well, it's a constant, so if I go back, that should have been a linear equation. If I go back again, that should have been a quadratic equation, if you think about the progress as you go through taking derivatives. Okay, but so I just wanted to explain a little bit about kind of where this Galileo's formula comes from. So let's go ahead and do an example. Let's say that, I'm going to go ahead and go to a different sheet here. Let's go ahead and say that an object is launched vertically from a, let's do a 100-foot cliff with initial velocity of 320 feet per second. Okay, and there are a few different things we're going to want to find here. So let's just go ahead and, okay, so some things that we want to know. Let's figure out the height of the object at time 2. And let's also figure out the velocity at time 2. And last but not least, let's figure out what the maximum height of the object is. So I mentioned here before that all of these are going to have this general shape, and so we can look and see when, you know, we might want to know the highest point that the object went. Okay, so let's start with the height at time 2. All right, now what's going to be really handy here is if we can come up with an actual equation or an actual function for the height, and that's what Galileo's formula will help us do. So I'm going to go ahead and write this part out again. We have the initial height, initial velocity, half of gravity, t squared. Okay, so let's see if we can plug in some of these different constants that we have. So the initial height, well, I was told that the object was launched from a 100-foot cliff, so that means that the initial height of the object is 100 feet. And the initial velocity, also something I was told, was 320 feet per second. And now I have this gravity over 2, so gravity over 2. And again, the reason I'm dividing by 2 is when I take the derivative, I bring this 2 down from the power rule. And I just want to get gravity when I'm done. If this part wasn't there, I would end up getting twice gravity when I get to the acceleration. So I need to have it halved there. Okay, so we have a few options because we could use the feet per second or the meters per second. And so this usually will have a choice that we, a clear choice of which one to look at. In this case, I clearly want the 32 feet per second because all of my other units are in terms of feet. So I would want to look at then 32 divided by 2, 16 would be my coefficient in front of the t squared. Okay? So that means that for my height, or the object's height at any moment in time is given by this function. Okay, so let's take a look then. We wanted to know the height at time 2. So all we just need to do is plug 2 in. Okay, so I get 100, 640, minus, that would be 64. So that comes out to 676. Okay, and let's think about what those units would be also. So this is the height after 2 seconds. So the height then would be in terms of feet. Okay, so that's pretty good. We started at a 100-foot cliff, and after 2 seconds, it had gone up to 676 feet. Okay, all right, so let's answer, this is part A. Let's answer part B. Now we want to know what the velocity is at time 2. So as I mentioned before, the velocity is the derivative of the height function. Okay, because again, this is the rate of change. How is height changing with respect to time? Well, that's the velocity of the object. So we can use the power rule to take the derivative from here. Derivative of 100 is 0 because it's a constant. Derivative of 320t would be 320 minus 16 times the derivative of t squared would be 2t. So that'd be 32t then, the 16 times 2. Again, that's really right there, that's our gravity coefficient, 32 feet per second per second. Okay, so that's our velocity. Now I want to specifically know what the velocity is after 2 seconds. So I'm going to use this function, plug in 2, I get 320 minus 64. Okay, and after that I get 156. No, that's not right. Sorry, 256. Okay, and the units here would be feet per second. Okay, so feet per second because we're talking about velocity. We're talking about the change in height over the change in time, so those units would be in feet per second. Okay, so let's take a look at also the maximum height. Okay, so let's just come back here to the kind of general picture that we had for an object under the influence of gravity. And I want to know what the maximum height is, and I can see that that's this point right here. Now, there are a few different ways of finding that point. We actually do have you could use the quadratic formula to find the zeros and then kind of go halfway in between. But one thing that I'm noticing is that at this point, this is when the object changes from having positive velocity to negative velocity, right? Because at first it's going up and then it changes to going down. So at that moment in time, and we can also see this visually, the velocity here is 0. The velocity is 0 at that maximum point. So that might be a good way for us to actually find the maximum point, or at least for us to find when it occurs, is we can figure out, well, when is the velocity equal to 0? So let's come back over here. We have our velocity equation, 320 minus 32t. And if I set that equal to 0, well, then that'll tell me when the velocity is 0 or when we're experiencing that horizontal tangent line. That would be at the top, at the maximum point. So let's go ahead and solve this. Let's add that 32t to the other side, and then we can divide both sides by 32, which I can see would end up being 10. So then that means after 10 seconds, when t is 10 seconds, that's when the ball has reached its maximum height. So if I were to draw this, it looks something like that. And this height would be, or this time, I mean, would be at 10 seconds. Again, we see that horizontal tangent there. Okay, but that's not actually really what the question was. The question was, what is the maximum height? I did find out when it occurred. That is definitely one kind of component to it. Now, I'd like to actually find out how high the ball was at this particular moment in time. Well, that would be given by the height function, right? This function tells us how high the object is at any moment in time. So if I plug in 10 in here, so I'd have 100, 320 times 10, 16, 10 squared is 100. So I have 100, 3200, 1600, and I end up getting, after all that, 1700. So 1700 feet. It's So that means then that the y-coordinate here is 1,700 feet. Went pretty high, pretty good for starting at 100 feet. Okay, so being able to create this function really helped me to answer a lot of questions about the object. Notice I wasn't really given that much information to begin with. I was told the height of the cliff and just the initial velocity that it was launched, and I was able to answer all of these different questions just by using Galileo's formula. Okay, one other thing I'd like you to notice, and I kind of mentioned this a little bit already, but if I take the derivative of velocity, that would be the acceleration, and I see from here, here's my velocity function. If I take that derivative, I'll just get that negative 32 feet per second per second. So again, this is the acceleration due to gravity. Well, let's see. So I took the derivative of velocity, but velocity was a derivative itself already, right? Velocity was the derivative of the height function. So what I've really done when I talk about acceleration is I've taken the derivative of a derivative. So that means I've taken the second derivative. So actually, let me write that out. Acceleration is the second derivative of the height function. Okay, so one way that we can write that, because maybe I want to write the acceleration function in terms of the height function, when we talk about a second derivative, instead of putting just one prime there, that would be the first derivative, we're going to put 2. That would be the second derivative. Okay, so acceleration is really the second derivative of the height function. And I'd like us to go ahead and talk a little bit more about these higher derivatives now. We've had experience with one derivative, but we haven't quite done multiple derivatives yet. So in this case, this would be the second derivative, but we could keep going. We could do the third derivative, the fourth derivative. There's really no limit to how many derivatives we could take. So let's talk a little bit more about higher derivatives. And the thing I'd like to talk about mainly is the notation that we have for that. And of course, we've been experiencing 2 different types of notation. So let's go ahead and look at both of those. So let's start off with kind of the derivative, that is the number of derivatives that we want to take. And then we'll look at prime notation, and we'll look at Leibniz notation. Okay, so let's start with the 0th derivative. Okay, so that is not even taking a derivative. Well, that would be then just the original function. So in prime notation, we generally use function notation. In Leibniz notation, we tend to use just the variable y. Okay, so let's take a look at the first derivative. We've had experience with that, f prime of x dy dx. Again, this is kind of like the change in y over the change in x, just like slope. Second derivative, okay, so we just looked at that one up here. We'd put 2 primes there instead of just 1. And now the Leibniz notation, well, think about this. We're taking the derivative of the derivative. Okay, that is, I'm taking the derivative of this dy dx, the derivative. So notice that when we do that, if you kind of think about multiplying across, we don't really want to think of this as a fraction, but sometimes it kind of works out in terms of notation. If you kind of think about multiplying across here, I have 2 d's, so d squared and a y, all over a dx dx, so that would be dx squared. So this is the notation we use for Leibniz. We have the 2 in between the dy and then the 2 on the outside of the dx. Now technically it is like a dx squared. That should be, we don't really put it in parentheses, we usually just leave it as is. So that's notation in Leibniz form that means the second derivative. So up here, I could have written this as d2h over dt squared. Okay, so the third derivative, we usually do three primes for that one. And here I'd have d cubed y over dx cubed, like that. Now, right around the time we get to the fourth derivative, it just starts getting to be a bit too many of the primes. So instead, we start putting the actual derivative number that we want in parentheses, where the primes would normally go. So this represents the fourth derivative. This notation is very consistent. It pretty much stays the same, and I've kind of gotten a little bit off in my rows here. But, so this one would be dy, 4 there, x to the 4th. So this one's pretty consistent across the board. If I were to go to the nth derivative, I'd have f of n. So that would be the nth derivative, and this one would be written like that. Okay, just some different notation. All right, so let's just do an example of looking at a higher derivative. So let's say that I had the function x times e to the x. And let's say I wanted to know what the 78th derivative is. So I'd write it like that. What's the 78th derivative? You might be thinking, oh wow, this video is going to be really long if she's going to calculate the 78th derivative. But let's just start with the first, second, third, etc., and see if maybe there's going to be a pattern that that emerges that we can use to our advantage. So let's start with the first derivative. Now I see a product here, so that means that we need to use the product rule, right? So the product rule says we take the first thing times the derivative of the second, derivative of e to the x is e to the x, plus the second thing, e to the x, times the derivative of the first, so the derivative of x is 1. Now from here, I could see that, well, maybe it'd be easiest if I kind of think about factoring out this e to the x. And one of the reasons I kind of want to do that is because that will allow me to only have to do the product rule once the next go around. So I have x e to the x, so I'd have an x here plus 1. Okay, so I just went ahead and factored out an e to the x. Let's go ahead and take another derivative. So now I'm taking the derivative of not this part, but the derivative of the first derivative to give me the second derivative. So again, using the product rule, I have the first thing. Derivative of the second, well, the derivative of x is 1. Derivative of 1 is 0, so I just have e to the x times 1 plus the second thing times the derivative of the first, and that would be e to the x. Let's go ahead and simplify this again before we go to the next one. I'm going to pull an e to the x out, and I can see that I'd be left with a 1 plus an x plus 1. So combining those in the parentheses, it's the same thing as e to the x, x plus 2. You might be seeing a pattern. Let's just go ahead and do one more for good measure. So now I'm going to take the derivative of this. So I have the first thing, the derivative of the second, plus the second, times the derivative of the first. And I can see that I can again pull that e to the x out. I'd be left with a 1 plus x plus 2, e to the x, x plus 3. We start to see the pattern then. First derivative was e to the x, x plus 1, e to the x, x plus 2, e to the x, x plus 3. So I can kind of see that if I do the nth derivative, it should be e to the x, x plus n, right? I'm kind of seeing that with the pattern. So then the 78th derivative would pretty simply be e to the x, x plus 78. So not so bad. That's one of the great things about seeing a pattern is we definitely had to do much less work. We only had to go to the third derivative in order to get to the 78th derivative. So there are lots of applications to higher derivatives, and we'll continue looking at that.